think I have more bugs presented in the slides than the proceedings, but you should be able to follow it with the proceedings as well. So my presentation for today, kernel auditing and exploitation. So there are three parts to this presentation. At the end of each part will be questions and whatnot. The first part is kernel auditing research. The second part, just a sample of exploitable bugs. And the third part will be the exploitation of various bugs. Like I said, questions at the end of each section, but jump in if you've got any questions in any part. So part one is kernel auditing research. Just an overview of the auditing work that I've done in the past. It was this particular audit, manual audit of the open source kernels. The open source kernels in question being FreeBSD, NetBSD, OpenBSD and Linux. And the reason for these was primarily just availability. You can download the sources, so why not audit them? And the auditing was for about 3 months. It was part-time, not a full-time audit. Like, didn't spend all my day auditing code, but when I had free time, go ahead and audit some. So it's July to September last year. It seems, slightly outdated, I suppose, but it's not really. A lot of things still apply. There's even some zero-day which I presented a couple of months ago, which still never got fixed. It's a lot of interesting things to talk about. Just to give a time frame of the auditing that I did on each operating system, NetBSD was about a bit under a week. FreeBSD also a bit under a week. OpenBSD not too long, and Linux was pretty much the rest of my free time. And the reason for this was I use Linux a lot, so I don't know. I suppose I was a bit biased and wanted to audit it more. So what prior work has there been done on kernel source in terms of auditing and vulnerabilities? Dawson Engler, in the past couple of years, has released some great papers with automated bug checking, like the Stanford bug checker, which it's commonly referred to, the automated bug discovery that Dawson Engler's worked on. It's been run against various open source kernels, and they've found a large number of bugs actually through automated means. I was just getting some weird. Okay, so the Dawson Engler's work found a lot of concurrency issues and synchronization issues. So we're looking at things like double locks, double unlocks. Found a lot of those. Also did a lot of things on double freeze as well. Found a lot of those. Did find some buffer overflows, but in my opinion, the most bugs that came out of the Stanford bug checker were in relation to concurrency. Some other prior work as well is the Linux kernel auditing project. Got a question mark at the end of that because, as far as I can see, the Linux kernel auditing project, or LCAP, really didn't do anything. I don't see that the Linux kernel has been really audited. I think LCAP released maybe 2 advisories, and the mailing list is about 3. Not so many comments, and most of them seem to be saying, let's audit the kernel. There isn't actually auditing there. It's just let's audit the kernel. So that's a bit unusual, I think. Just some notes for the presentation. When I'm talking about bugs, I'm just really referring to vulnerabilities and security bugs. I like the word bug I don't want to say vulnerability for every single bug. So unless I say otherwise, every bug is in relation to security. After 3 months, at least 100, maybe up to 150 bugs were patched in various kernels, across all the kernels. Still a lot of bugs in there, but see how it goes. So one of the things I wanted to talk about is, there seems to be a lot of myths about the kernel and stuff. It's I've talked about this, like kernel security mythology. It seems that people think that kernels are written by security experts and programming guys, and there are great programmers working on these kernels. Like, there's no doubt about this. But when looking at tens of millions of lines of code, the follow-up to this myth is, therefore, kernels don't have simplistic security bugs. They don't have security bugs, and if they do have security bugs, they're just, they're not simplistic. And I'll try to show evidence to that contradicts these myths as we go on. Another myth, which is just a follow-up on the first one, is that basically the rewrite of the first one, that kernels don't have simplistic security bugs. Therefore, only security experts or programming guides can find them. Maybe you see something in an advisory that says, not even any advisories to be honest, something that says you have to do this in a certain condition. If all these things apply at once, maybe it will be vulnerable. And it seems not to be the case. There are a lot of simple ways to exploit kernels. Another myth, this is the third and final myth that I'm going to talk about, is if kernels are buggy, they must be so difficult to exploit, and therefore exploitation is probably just theoretical. Maybe you can do this, and maybe it's possible, but so many conditions are required to cause exploitation. And for me, that doesn't seem to be the case from my experience. So I'm basically putting forward some conjectures at the start of the auditing project, let's say. Kernel code, it's not special, it's just another program, a really big program, but just another program. It's written in a language with known problems. It's, all the open source kernels are written in C. And C has known problems that time and time again, you're going to see, buffer overflows. You're going to see integer overflows. You're going to see a lot of problems. If we look at kernel programmers too, they're just people. And sometimes they do make mistakes. It's hard to say to someone, 10 million lines in a kernel, are you sure 100% that, that you didn't just skip something or overlook something while writing it? So the way I went about auditing was that I'd only audit for simple classes of bugs. I wasn't looking for incredibly complicated attacks. If we look back like in the past month or so, 2 months I think, there was a paper that was released about hashing collision attacks. If we could for example, Linux, if we could send a certain sequence of packets, these will all, when they're hashed, they'll all collide, and essentially the complexity of a search would, break down into a linked list, a linked list search in linear time. And, this was like, this was an attack here. I'm not looking for such complicated attacks. Looking for simple attacks that, easy to find, easy to grep for. And incidentally, with the hashing collisions, a while ago actually, Solid Designer in one of the earlier frats also talked about hashing collisions, very briefly, but talked about when writing scanlogd, that one possible attack on it and attack on all IDSs was that if you construct certain sequences of packets or data, then you'd have these hashing collisions and the complexity would get really bad. Everything would be a worst case scenario. The paper release in the past few months was really good and really strong mathematically. But again, I'm not going for those attacks. As with most audits, I suppose, as you start to audit, you start to see patterns or start to see classes of bugs that lead on to other bugs, and you start to generalize of what might be another attack or a class of attack. So if you look at just some of the experience that was attained, I suppose, system calls are simple entry points into the kernel. This is really what what I'm grepping for. Looking for entry points in the kernel which are easily controlled by userland. System calls are the obvious one, and in some ways possibly they're overused by people that are looking to audit the kernel. If we look at device drivers as well, basically these are by design simple entry points into the kernel. Device drivers for Unix, everything is a file, easy access to the hardware through a file. And some people, I suppose, would argue that one of the downfalls of Unix, and was IOCTLs. IOCTLs are just so general purpose. They're Swiss Army knife. They do everything under the sun. And it seems that IOCTLs tend to be a big problem in terms of the number of bugs when implemented in device drivers. Device drivers, in my opinion, seem to be the most buggy parts of the kernel. Core kernel code seems pretty good, but the number of device drivers out there that have bugs are just amazing. So immediate results since started auditing. First bug found within hours. And this was true for all operating systems that were audited. And it's arguable that the first bug is often the hardest to find. But also must be taken into account that it was a targeted audit. I was looking for specific, bugs. I wasn't just starting at admit.c and working downwards. So some observations. There does seem to be, varying degrees of code quality, and hence security bugs. Again, core kernel code seems to be pretty well written. Device drivers, anyone can really submit in a device driver for a particular piece of hardware, and you can't really guarantee that. It seems to be a lot of bugs in the device drivers. Okay, here's an interesting thing. Bugs, they seem to exhibit this sign of propagation in the sense that if you have a bit of source and it becomes the reference source, everyone uses this source as the base source to how to write something. And this reference source has a bug in it. This bug now seems to just, verge into other parts of the sources. And clustering also, it's in the sense that it seems that once you find bugs in a particular area of the source, more bugs are close to that area. And this is really like just supporting the work of Dawson-Engler and automated bug checking. And that's why I've got the asterisk there, because there's another slide shortly after. There are identical bugs in all platforms. Some of the code is basically the same in every platform, and some of the bugs are exactly the same. And I should have slides to show this as well. I do have some bias in my auditing, of course, because manual auditing is inherently biased. Maybe, I believe that the core kernel code is secure. That's why I'm not finding any bugs there. Maybe I think it's just device drivers that are buggy, and it's a self-fulfilling prophecy. I can't, definitively say, that this is true. I can just show evidence to support, what I'm trying to put forward. Dawson-Engler's work, on the other hand, is automated and avoids the bias of manual auditing. So here are some observations. This is going back to there are the same bugs in all platforms. So what we have here is NetBSD and OpenBSD. And I should actually say that I haven't included enough information here to actually to show people that this is exploitable. And it was actually Norman over there came up to me earlier today and said, where is the bug here? So if we look at start and num are both signed integers. So the basic idea is that we make start plus num a value that wraps around into the negatives. Later on after this code, we have a buffer overflow that uses the result of num or start. It's a bad example because I don't show the buffer overflow here, but integer overflows are pretty much everywhere. We've got plenty more to show. So I'll show some evidence in just contradiction to the kernel mess that I presented. Kernels aren't written by gods. They are written by people, extremely talented people in many cases, but still people. The initial bugs are found in all hours, found in hours in all kernels. It should be in all kernels, I suppose. Bugs were found in large quantities, 10 to 30 per day was one. OpenBSD was only a couple days of auditing, and there were a reasonable amount of bugs were found in that. Likewise for NetBSD. In some, if you do go looking for bugs in the kernel, you will find them. 2.6 test kernels, I do believe, do have some quite similar bugs to the 2.4 kernels and the 2.2 kernels. There's a lot of bugs that are still out there. Now here's something interesting. In some parts of the code, we saw inline documentation. The state of the code was secure, and in fact, often it wasn't. I'll just show this. I don't think you have this in the proceedings, but it's a pretty funny comment. So basically, this guy has written a device driver. I think it's in the video for Linux code. So basically, it says first things first. Make sure we don't copy more than we had, even if the application wants more. And then he states that would be a big security embarrassment. And then the very next line, he's got an integer overflow. Okay, so it's 2 lines later. It's exploitable with a copy to user. And we can copy pretty much arbitrary kernel memory back into user land. Count is under our control in this example. Likewise, we have partial control over secread_index, and then in our copy to user, providing we make count large enough and we get a wraparound in the first comparison, we can copy a very large amount of memory, copy it to userland. Yeah. So Linux 2.16 has another funny comment. This comment says, this routine does error checking to make sure that all memory accesses are within bounds. And in fact, there's actually multiple problems with this code. Bus size is a signed integer. So initially we just have to make bus size negative. Get user ref on the top, if you guys can see that, actually copies from userland a value into bus size. So we control bus size. And we can make it a negative, pass the next test. In the kmalloc we have integer overflows anyway, and then down below we have a buffer overflow. So multiple problems with this, even though the comment is to make sure that all memory access is within bounds. So I just want to show evidence in contradiction to that there aren't any simple kernel bugs. Almost never was I required to do like intensive code tracking. Grepping for bugs, grepping for likely places to exploit. Found a lot of things. Very close to it. Grep for a copy to user, copy from user, copy in, copy out. Right above there, look for something that might be buggy and hence probably exploitable. And in some cases, no input validation at all. Even inline documentation shows that non-working code exists in many places. So this is IBCS2_stat.c. Basically, we're doing a copy out at the bottom. This code applies to all the open source kernels. It's similar pretty much in every one. We do a copy out of len bytes, and len has just no input validation at all. You can put anything you want for len and copy arbitrary memory back to user space. We have another case where this looks like to be NetBSD or OpenBSD. Some of the drivers share bugs, and I should have put which OS they really all apply to, but there's NetBSD, OpenBSD here. If we look at count, we do a copy out with count. This copy out is called basically from an IOCTL. There's no input validation on count at all. We can copy arbitrary memory again. We do have to be on the console, which it's not too bad at that point, but essentially there's just no input validation. This is a good bug in Linux. It's actually a bad bug, I suppose. I actually released this bug and an exploit for it a few months ago at RuxCon. It's just never been fixed since. It's never been fixed. We have XXX untested. And basically, the code below cannot possibly work. The arguments are wrong. It should panic the kernel if this code ever gets called. I suppose it's, just before it sounds like I'm really bagging the kernels here, but in general, they're pretty good, I think. And vendor response was excellent. So many bugs were fixed. And really, if we think that other code doesn't have problems, very naive as well. So I'm showing some examples here that there are such simple bugs as there are in many much software out there. So I just wanted to say that before before going too much into bagging any kernels, because I do think that open source is pretty good. So some more evidence in contradiction to the kernel mythology. If kernels are buggy, they are sometimes reasonably simple to exploit. To read arbitrary memory from the procfs, using the procfs actually, in Linux 2.2 and early 2.4, or most of the 2.4s actually, 38 lines of C, and it's 100% reliable. Likewise for FreeBSD accept system call, which an advisory was released last year, 37 lines of C and 100% reliable also. Incidentally, the Linux people do have the exploit for the procfs code. I did send it to them, and I also did send the FreeBSD people the accept exploit as well. And I'll actually show the accept exploit later on in the exploitation part. Okay, stack overflows. In Linux, for example, they don't require any offsets. Kernel stack overflow does not require offsets. It's pretty reliable. I'll show some shellcode later on, and the only assumption is that the return address that we're overriding on the stack is word align, and that's a pretty good assumption. GCC will word align return addresses. We control userland completely. We control all offsets in userland and addresses in userland pretty much. So there isn't anything to brute force. Very reliable. So attack vectors. It's back to there's more code running and more code accessible. You're probably going to be you're going to have more exposure. Don't run bloated generic kernels. Recompile your kernel. Don't compile support for any hardware you're not using. If you have device compatibility with a million devices, possibly one of those devices might be the software for it might be exploitable. And it's all back to that entry points that userland can control. These are vectors of exploitation. So I've got some examples: device drivers, system calls, file systems. For example, with file systems, with the procfs bugs that were in Linux, if you seek to something like, if you open a file in the proc file system that's readable, and many files are, you could do something like seek to around 4 gig, just below 32 bits. This is for i386 specifically for 32 bits, but it's quite generic. And then if you say read, for example, something with the count that when added to the file pointer will cause an integer overflow. And at that point, many things become exploitable. And it turns out that such an attack was quite generic against a number of files in the procfs for Linux. The vendor response. Vendor response was really excellent, to be honest. All contact points responded extremely fast. Theodorat did respond in under 3 minutes. I sent an email with about a list of 10 to 15 bugs. I turned around to having a conversation, turned back, and received an email from Theo with responses to those bugs. Alan Cox, I think I put in the proceedings 2 hours. I do have copies of all these emails and massive lists of bugs that were sent in. Alan Cox was extremely good, responded back in a couple hours with statuses on all these bugs. Initially I sent a list of bugs for 2.2.16 kernel, and the current at the time was something like 2.4.18 I think. So Alan Cox could go through all these bugs in 2.2.16, say, yes, this has been fixed at this point in time. This one looks, this one is valid. This one doesn't look valid. Did include a few false positives with my auditing, and I thought that was a fantastic response by Alan Cox. So even replied that Solid Designer had fixed some get-sock-opt and set-sock-opt bugs back in later 2.2 actually, from a year or two ago. So that was exceptionally good, I thought. I am a bit biased though, because I really do believe in open source. I do think the vendor response was extremely good in this case, but I am a bit biased, and I suppose it's arguable that I was emailing developers directly, not going through any super official contact points, and they responded back immediately, discussing code. Okay, a bit more bias. Bad joke, but a lot of hacks on the Linux kernel. Yeah. Okay, it was a bad joke. Okay. So there's 106 references to the word hack in the credit section. But they like to use this terminology, hacks on this part of the code, hacks on that part of the code. So it's pretty funny though. Just to talk about Linux a bit more, Alan Cox was the first person I contacted. He remained personally involved and really responsible, for the entire duration, sending a lot of stuff, and would, always respond, immediately. Would always be, up to argue over bugs and say, I don't think that's exploitable. I don't think, that's valid. And many times we're like, totally right. Just, ignore that. And Alan Cox did patch the majority of software. He did attribute me with some small with patches in the changelogs, for things like one or two line changes, just doing checks on various signs or various overflows would attribute me to that, but ultimately he did do all the pushes back into the mainstream kernel and actual writing of the code there. Solid Designer was responsible for the 2.2 kernels. He got involved a bit later on after initial contact with Alan Cox. So actual Solid Designer was responsible for the 2.2 kernel release. The later one that came out, I think last year, I can't remember the month, but after like about a year or something of not releasing 2.2, Solid Designer did backput pretty much all the 2.4 bugs and everything that was applicable, introduced other fixes as well. Dave Miller also helped out later on, did initially work primarily on the Spark stuff, does most of the Spark stuff and network code as well, but also helped generically as well in a number of things. So in my opinion, I think Linux was successful. Red Hat actually released an advisory last year, and they actually mentioning the DMCA and saying things like, well, we can't really say what vulnerabilities were fixed, and we can't show you the code because of the DMCA. And if you go to this website, which is outside the US, and you can see the patches that went in. But ultimately, I do think Red Hat and pretty much all the Linux vendors now have been totally successful. They do regularly release kernel advisories now. And in my opinion, that was probably attributed to the work we did last year. It's ironically, the Linux audit was probably the most complete. There was code in there that obviously had never been looked at before, and it's ironic considering that the Linux kernel auditing project was there, but it does seem to have been the most complete, even if just the sheer number of lines that were looked at, or grepped at least. FreeBSD has a more formalized process with patching software and security problems as a security officer contact point. Dialogue slightly longer to establish. It's very effective once up and running. I'm talking about address standardization issues here in this slide, and what I'm referring to here is that there was one particular bit of code with the accept overflow, and basically the from length in the accept system call was sock address socklen underscore teal, and basically this was a signed value in the kernel, and really why would it be signed? This was a considerable issue. They did change it to be unsigned. Linux with the get sockopt and set sockopt kept their socklen underscore t, sockoplen underscore t, sorry, as a sign, and that's, in my opinion, just making things unsigned when they have to, when they are going to be unsigned, solves a lot of issues. It's unfortunate, but it seems to be the case. A lot of signed problems, in a lot of code. So making things unsigned, is actually useful. Was FreeBSD a success in terms of auditing? I don't know. Nothing really changed with FreeBSD. They did release an advisory for the accept thing, and at the time I was working in this vulnerability assessment company. A co-worker came up to me and said, I'm going to implement your vulnerability today. I'm like, what are you talking about? What vulnerability are you talking about here? And he's like, FreeBSD have released an advisory. I'm like, oh, okay. So that was pretty unusual, I thought. I didn't ask them to release anything there, but they did release it, which was, I think pretty good of FreeBSD. The reason for this square on my slide is because this is OpenOffice and it's a PowerPoint import, and the smiley face didn't go across because it doesn't have the font. Okay, so NetBSD, the dialogue with them wasn't lengthy, but all issues were resolved. After a small waiting period, I was actually sent them a list of bugs and was watching the change logs to see how long it would take before they said, yeah, we'll put them in, we'll fix all this. And I was just watching the change logs to see pretty much how many days it would take. And it seemed that what happened was, one of the developers did a bit of personal QA, then ran it on his own box, waited a bit under a week, and then pushed it into the unstable development version of the mainline kernel, and that seemed pretty good. The patches, surprisingly enough, there was some shared problems in the drivers between NetBSD and OpenBSD, which isn't really surprising if we consider that OpenBSD was initially a fork from NetBSD. Some of the drivers do share, there are shared bugs there. But the patches just propagated very quickly from NetBSD to OpenBSD. Looking at the change logs for OpenBSD, I'll have change logs from NetBSD. So OpenBSD, probably the quickest response, in documented history. I've never seen, 3 minutes to respond to these things. An OpenBSD select advisory was released shortly after that, actually, and I didn't actually audit or report a select overflow. I did pass it a little bit, but I wasn't only looking for simple bugs here, and I didn't want to follow the macros. But it seems that the OpenBSD started, doing, auditing after that because Niels Provost released an advisory for it, a bit after that time that I sent them a list of kernel bugs there. So this is sort of interesting, and I suppose it's a small go at OpenBSD. So if we look at the IBCS code, which I showed before, which had no bounds checking, no sanity checking, input validation at all, it's actually regarded as a possible integer overflow. So I'm not exactly sure, where that comes in. There's also some other interesting change logs when they talk about possible integer overflow. Some of these are okay, but have been changed for consistency, and they're all exploitable. So the IBCS2 _stat.c code. Linux has fixed it, OpenBSD has fixed it, NetBSD have fixed it, FreeBSD have not fixed it. I don't know why. I really didn't, push after I didn't really push hard for that. And it's still, there's no input validation at all though. So today, where are we in kernel security? Auditing always results in vulnerabilities. It always does. And auditing and security, it really should be an ongoing process. You can't just say that, audited once, hence, secure indefinitely. You really do have to audit it, on an ongoing basis. And there's certainly, a lot more bugs than I'll describe today, and many ways of exploiting a kernel that, that I will describe today as well. But this is just the tip of the iceberg, in my opinion. So about 4 months ago, released, most of the technical results, lots of bugs, lots of patches, and I released an exploit for the COF binary loader for current Linux at the time and current Linux today. Also released, also showed the stat.c code, which just had a couple slides ago. But they're still present today in all the in the kernels talked about. So it's a bit of a question there. Does anyone read conference material besides us? If you're not at the conference, will it get fixed? So that sort of is the conclusion of my first part, the first part of my presentation. Are there any questions? Yep. No, it's a really good question. Dave asked me if the COF binary loader is default on Linux. No, it is not default. A lot of the stuff that I'm presenting isn't default. If we look at, there are bugs in like the ELF loader has some integer overflows, but I've not exploited or exploited anything to any great extent, and there are some problems that seem theoretical that should seek further investigation to see how they'll go. The a.out loader has some integer overflows as well. That had actually a bug fixed in it last year as well, with you could escape R limits due to various integer overflows there. The a.out code actually has so many integer overflows, but most of them are just integer overflows and they don't do anything. I think I've only looked at the Linux code for the shell script passing. Basically, when you when the kernel looks at a binary or a shell script and it tries to pass the hash bang, it actually does a lot of work because there's white space, there are tabs, and it has to fit some certain requirement before it can execute this shell script. So I think maybe in other systems it might be exploited because it's always a bit scary when there's parsing involved of weird stuff in the kernel. Okay, So the next part of my presentation is just a sample of exploitable kernel bugs. So I've got actually more on my slides than I do on the proceedings, but there's some interesting ones in here. This was one that showed earlier, and this also isn't by default in OpenBSD. It has an ifdef user LDT. I talked about this a bit before, and I should have included more, and it's the worst presented bug that I've got here, since it doesn't show all the features that make it exploitable. Start plus num can overflow to get sign conversion, so we can actually make that a negative. Start plus num becomes a negative value, which will be less than 8192, and later on in the code there will be a buffer overflow there. This one is a good integer overflow, because this one has occurred in a lot of drivers in OpenBSD and NetBSD. So we make a check at the top. Can everyone see that okay? I'll assume so. We make a check that if count, if it's 0 or index is greater than or equal to 256, then we return. But index plus count. Count is basically any large value at this point, any number not 0. So we can make count, something like uint max, and make index 1, make it 1, and then we'll get an integer overflow at the highlighted line. Later on, we'll have a copy out using count, which is our large value, and then we'll have a memory disclosure for the driver, for the kernel in general, actually. Another one here. This one has another integer overflow, and it's a good integer overflow because it shows like a common class of bugs that people are allocating memory using one expression, and then later on they'll do a copy a buffer using another expression. And it seems that it always causes problems when people are using two different expressions when they want to do the same thing. In the first case we can get an integer overflow and produce a small value. In the second case we can use a large, we get a large value. This always causes problems in all code. As soon as you have like checks using one expression and copies using another, it's a very likely place of compromise. This one here, we have a sign problem. We take the minimum value of a syscall argument and another value, and it turns out that length is a signed value, so we can make length a negative, and it will turn out to be the minimum. So we'll have a negative value which turns into a large positive value in the buffer copy, and we'll have another buffer overflow copying memory back into userland. This one here is good in the sense because we have count times, we have A times B, and this we can get an integer overflow to occur, make it a small value, and then later on we'll do an iteration using one of those values, which can conceivably be very large, and in our first case we'll have a very small result. So we have inconsistencies in what they think is happening. The bug here occurs, of course, in the loop itself, since count can be very large, and count times size of block info can become an integer overflow there. If we control count, which we do, although I might have I think I've skipped some of that code there. Okay, so like a lot of these bugs are just slightly modified versions of sources that I sent developers directly, but it's been modified for presentation today. This one again is very much like the last one. We have a syscall argument called dev, which is a signed integer, and then down below we have a comparison that says if this value of this value dev is greater than hostname len, then bad things happen. But if we make dev a negative value, then we can pass that check no problems. And when we go to the copy out just below it, we have a very large value copy buffer overflow again. I should also include that hostname len is a signed value here. There are problems if you do things like comparing signed and unsigned, because you'll have like sign conversion. If you compare a signed value and an unsigned value, and they're both of the same rank, like a signed int and an unsigned int. Better example, a signed int and a size of. What happens in GCC at least, and this apparently is part of the specs, is that the signed value will be converted to unsigned. So in some cases that saves code, in some cases it breaks code. The specs are pretty ambiguous at this point. They say that size of returns size t, and size t is just some unsigned, an unsigned integral of unsigned integral type. It doesn't say if it's a short or a long, or what it is. So it's an ambiguity of the specs here, in my opinion, because if you do something like compare a long signed with just an unsigned int, then you won't have the sign conversion. So it's a bit ambiguous in my opinion, and it does cause problems. I haven't talked about that too much here, so it's not really necessary for the rest of the presentation. If we look at this code here, we have power write file, which is part of a device driver. Presumably you have to be a super user to do this, since typically you would have file permissions stopping arbitrary users from writing to such a configuration file or so forth. But if we look at if count is less than or equal to 0, the less than 0 is quite redundant, since count is unsigned to begin with, so it will never be less than 0. GCC will just not include this part of the code in the code generation. Doesn't want about it either, so it's silently delete stuff, which is quite fine, but it would be nice to have a warning or something. So basically for this one, if we make count of size uint max, when we have count plus 1, we'll get an integer overflow and we'll allocate 0 bytes. And in the kernel, we will actually get a successful result. It will return something. And then we go to copy from user. Count being of uint max size will be a buffer overflow there. It's probably going to panic the kernel there. But again, it's only for super user. But it's a good example of some of the bugs that are seen. Okay, I think I'm running going really slow. Well, not really slow, but I'm running really long here. Okay, so if we look at this one here, this is an interesting bug because it affects much of Linux 2.2, 2.4. So we have int off equals, and we cast the offset, and we have a comment next to it saying avoid useless 64-bit arithmetic. Now this is a problem that I was mentioning earlier when we have a 32-bit file pointer, and we seek to just around 4 gig, and then we try to read something that will cause an integer overflow. So when we have off plus count here, the offset we can control by an lseek, and the count we can control by just a read. So in this case, we will get an integer overflow in off plus count, and essentially do a copy to user down below with really count that's under our control. So if they had actually deleted that line that said avoid useless 64-bit arithmetic, they would have been safer, but not entirely safe, because I think in the next example, actually no, I will just go back. On 64-bit architectures, count can also be 64-bit. Size t can be 64-bit. So if we have the offset, the file position, the file offset is 64-bit, and on a 64-bit architecture, size t is a 64-bit, we can once again get an integer overflow. So you really do need to add a check to say, is there an integer overflow here, as opposed to just keeping everything as 64-bit and different architectures that will be exploitable. In this code here, I won't talk about this one for too much. Without going through the details, basically we call a function using count initially as an unsigned, and then in the function that we're calling, it sign converts it to a signed value. And at this point, we can take a minimum again and use this negative value to go back to the original function and cause a buffer overflow again. This one is another procfs bug, and we have off underscore t for offset, which again is the same problem as before. The problem here, there are a couple of problems, but for starters, they should have used l off underscore t. So it's actually an integer overflow plus a prototyping problem here as well. We have the get sock-opt code that I was talking about earlier, and basically this is a sign problem again. We're taking a minimum of a value that we control, which is our sock length, sock option length, and we copy to user. This one is a memory disclosure bug also. This one, I'm just going to go through these a bit, like not so in depth, but if afterwards, it just seems that I'm running really long, so I'm just going to try to get through as quickly as possible. This one you have to be super user, but the thing with this one, if you make length, if you write 0 bytes, 0 minus 1 will be uint max, and you'll do a copy from user with uint max here. So we have a check to say that if length is greater than line size, then there's a problem. But we don't actually check the case that when length is 0. And it's not normal to to write 0 bytes, but it's quite legitimate. This one is basically a sign problem again. We have short length. It should be unshort length. We have a check. Rio command.length, is it greater than page size? And if we make length a negative, we end up passing that check and causing a buffer overflow down below. This one is just considered really quite bad code for most people, because they're allocating about 1K on the stack in the kernel, which is considered don't allocate such large buffers on a kernel stack. You don't have a lot of room on a kernel stack. For Linux i386 you have 8K, so you don't want to allocate a K just haphazardly. Kmalloc would have been better, but if we make len a negative value, we can essentially cause a buffer overflow again. This one, another integer overflow. Again, because we're allocating using one expression, and then we're copying using another expression. This one, I think I've got 3 examples from this one particular file. This one is what I was talking about earlier. On a 64-bit architecture, even though we have PPOS is 64-bit, if we add another 64-bit value to it, we will have an integer overflow. So on 64-bit architectures, exploitable. On 32-bit, not exploitable. Okay, so I'm just going to pause for audience participation. Are there any questions at this point? Yeah? Okay, you just asked me a question when doing a copy from user. The return value on this call, what will happen if you can't copy that number of bytes due to problems such as you have page permission problems, or it turns out to be so large that what will happen. I'm actually at the very next part. I'm going to talk about exploitation. It's a good question, and I've tried to avoid the copy from user exploitation, the bugs particularly for that, in the sense of arbitrary, really large buffers. For Linux, you'll get some strange issues, when doing copy. So I'll just go through the next part of the presentation, which is all about exploitation, and we can come back to that or after the presentation. Okay. Okay. So part 3 is kernel exploitation. Okay. I really do have to I'm running extremely long, I suppose. Okay. So what exploit classes do we have that's available in the kernel? We can have arbitrary code execution, which obviously is the one that we're really after. And these, can have, uses such as, obviously privilege escalation, but, seemingly better uses such as escaping kernel sandboxing, security enhanced Linux, user mode Linux. If we are running in the kernel, we can escalate our privilege beyond what we have, beyond just a user land perspective. So we can avoid a lot of, a kernel sandboxing. Some other things of interest is like digital rights management. Say, for example, that we have a kernel that is signed at one particular version that only does one particular thing, which is play a video, play an MP3, but doesn't allow you to access from user land or copy it or do anything like this. Even though we've signed this this version of the kernel or version of this kernel, the distro, whatever we want to call it, if this software has these hidden features such as being exploitable, then certainly we can escape the DRM implemented at that level. We're looking at the kernel as our trusted base here. So if we exploit the kernel, then having a signed kernel or a signed userland, maybe trusted path execution in userland will help here, but ultimately it can break a lot of DRM things. We have another class of bugs such as information disclosure. We can read kernel memory. Definitely there's a FreeBSD exploit. And we might want to read things like SSH private keys. Root passwords, maybe we won't have so much luck with that. SSH private keys are certainly probably more plausible. There has been prior work done in kernel exploitation. And even though I just have this one slide for prior work, there's actually, there's been other work as well, which unfortunately I don't mention. So if we look at the last frac, we have smashing a kernel stack for fun and profit by Noir, and that was an implementation of an exploit from OpenBSD, the select overflow there. There's also been some other stuff done for Solaris, also FreeBSD I think as well. The Linux exec stuff of course. The Linux offloader from a while ago with the integer overflows and the program headers. But I think the problem is that people are seeing these as one-offs, one-off bugs, and there's actually a lot of bugs there. There's, we're looking at millions and millions of lines of code that no one's really audited. It's pretty open ground there. And we look at kernel implementation. All the major open source kernels are written in C. As I said before, language pitfalls are C-centric, not kernel userland centric. So, in my opinion, if you're going to audit something, if you're going to audit code, you shouldn't say, well, I shouldn't audit the kernel because it's the kernel. It's the same language here. It's just a big program. Audit it like a userland program. And there is no need to understand, in-depth kernel algorithms. Implementation is the target of attack here. We're not looking to exploit, weird, algorithms or weird conditions that occur when a million things happen at once. We're just trying to find language implementation attacks, such as buffer overflows, integer overflows, and so forth. C language has, well-known pitfalls. An interesting thing though to see that isn't present in other languages, in some languages, that it has undefined behavior in certain states. Like if we look at Java, probably a bad example here, but everything is, even error states, are defined. They're defined as being, an error state, not an undefined state. So when you have a buffer overflow or raise and etc. is an error, not an undefined state. Because in C, undefined generally means exploitable. It's the classic problems. Error handling, hard or difficult. An interesting thing is when we stop programming in assembler, what happened to the carry flag when we do addition? The carry flag is very, very useful. You can't really check in a high-level language. Did we have a carry then? Why don't we have that? It would be nice, in my opinion. We don't have exception handlings in integer arithmetic. An interesting thing is things like a lot of system calls and libc calls. They're both. If we look at malloc, for example, malloc returns null on failure. Null is generally 0, but 0 is a valid virtual memory address. You can mmap something that's 0. There's no reason why you can't. If you look at lseek, you can lseek to uint max, and it should return the file pointer, the position of the file pointer on success, and it does, but it returns -1, indicating success. So you can't actually tell at this point, and this is at a kernel level. It's not at libc setting error no. The kernel will return, reserves these negative values as errors. So if you lseek, to full gig, it'll do it in the actual code itself, the FS code itself. But when it returns back to userland, it does return -1. And libc checking error no, the system call itself, you can't do anything at this point. In my opinion, it wouldn't be such a bad idea to have error no, totally controlled by the kernel itself, and have thread-specific data or so forth that gets set by the kernel. And this would, an out-of-band error condition. It's unlikely to happen, but it's a bit of a wish list. From what I've seen, integer problems are just, they're everywhere in all C code. They really do occur a lot. if you look at a lot of source, you will see the same problems time and time again. Integer overflows are very, very common. Even things for like, checking error conditions. It seems, so simple, but how many people check for, out of memory conditions? It's quoted like that, the Linux kernel has no memory leaks, and this is true, in the average case. But there's certainly memory leaks in unusual conditions. And almost all code has memory leaks in unusual conditions. If it doesn't, some code will do, if an xmalloc, and if it's an allocation failure, it will exit completely. But if something needs to keep on running, pretty much all code, of all sizable code, will have memory leaks in weird conditions. Simply cleaning up, the allocations that occur beforehand, tends to be problematic. So what interfaces do we want to target when we are looking to exploit something in the kernel? The kernel buffer copies, very good place. This actually, Dawson Engler did a lot of the automated bug checking. Was very much a bottom-up auditing technique where he did look for kernel buffer copies, and then actually, I apologize, he looked he did a top-down approach from various entry points into the kernel, and then once reaching a kernel buffer copy, tried to establish if certain things could occur at that point. So if we look at a kernel buffer copying, kernel and user space can really be divided into two conceptual segments, user land and kernel land. So default i386 Linux, we're looking at 3 gig for the kernel, and 3 gig for user land, and 1 gig for the kernel. And we really need validation of our sources and destinations. So what I mean by that is, the code itself will check to say that you're not copying something from, let's say, the kernel land to the kernel land itself, or user land back in, you have to actually copy from user, should copy it from user land to kernel land. And there are segmentation checks on this to make sure this is the case. There are also, when we say, for example, we're writing to user land, copying a kernel buffer to a user land buffer, we need to make sure that the user land buffer is addressable. Is the page present? Does the page have permissions to allow it to write there? And incorrect input validation on these things, can lead to kernel compromises. And really, input validation, around buffer copying code is the target of exploitation that is present in pretty much all kernels. Okay, so I'm going to talk about kernel buffers here, kernel to user space copies. What can that provide us from an attacker point of view? It can allow kernel memory disclosure. So I presented a lot of examples earlier that if we copy something from the kernel to user land, but we don't bound that length, we can actually read arbitrary kernel memory. And this is true because of the case that partial copies of kernel memory and memory. So if you copy a buffer from kernel land to user land and you give it a very large length, say uint max, you don't actually have to have uint max addressable memory in user space. You can have 1 page, 20 pages or so forth. Page permissions and a page fault will cause the copy to abort early, but you will have copied that kernel memory to what you have available. And that's because verification of page permissions, they're not really done prior to the copy. In Linux, verify area can validate that you're copying to somewhere that exists, but it's mostly deprecated because it's better to use the MMU, the memory management, handle that directly. It will page fault when it tries to write somewhere that it shouldn't. So in effect, you can copy large amounts of kernel memory to user land memory, even if you don't have 4 gig of memory free. And the example here is that I've got the accept system call down below, and the from length is actually a negative value that I've given it here. The from address is actually a buffer that is about 1 gig. That's a bit large, I must admit. I put it in the BSS because don't really want to malloc 1 gig or put 1 gig on the stack. So the BSS is a reasonable place. You don't actually need to page in anything or so forth. Actually, it will try to copy 2 gig of memory to the buffer, but it will only fill 1 gig of memory. It will page fault after copying 1 gig, return back to accept, and should actually return an error. But at this point, we will have copied about 1 gig of kernel memory. Okay, so looking at kernel buffers now. Again, there are some optimizations that we can do. Let's check the top. There are some optimizations that we can do. We don't always have to check segments, so we don't always have to check that the segments, the kernel space, the kernel land is in the kernel land, user land in user land. What we can do is do a verify area initially on a buffer, and then we can put bytes directly into that buffer without any segmentation checks. If the assumptions that we make are incorrect, it's probably exploitable again. We have some classic exploitation here. Basically, we're creating a backdoor. We're going to set up a basically little kernel module that does a set UID 0 in a system call. We execute the system call, and we get a UID. We get UID 0 and privilege escalation. If we can copy this kernel shellcode or run this shellcode in kernel context, we can essentially exploit the kernel by this method. What do we do when we want to exploit something? We want to escalate our privileges, and we also want kernel continuation. We want the kernel to continue running without crashing. Privilege escalation, typically by manipulation of the task structure, process control block. So we want to change our UID, our GID to 0 to be root. Classic backdoor. I don't talk about escaping jails or chroot environments, which is another thing that is very useful with arbitrary kernel code execution. Kernel continuation. If we look at Noir's exploit from Frac60, went to a lot of work to return back into the kernel at a specific address. A specific address that would let the kernel continue running without crashing. And in my opinion, this was not the most optimal way of doing things. It requires a lot of knowledge of what's already there. It requires offsets and addresses. Essentially, it seems to be an overly complex method, and there are methods that we can use that avoid this problem completely. If we look at Linux 2.4 and kernel stacks here, every process pretty much gets an 8K kernel stack for i386 Linux. At the top of this kernel stack, we have our task structure, which is our process control block containing information about the process that's running. Contains information such as our UID, our GID, and so forth. It's very essential. The task structure, the current task structure, is relative to our stack pointer. So we can actually, once we're running in the kernel, we can look at our stack pointer and we can get our task structure immediately. And we do that by masking off the lower bits. And this will give us the top of the stack in our kernel stack. Okay. The next thing I'm going to talk about is ret from syscall. Basically, return from syscall. If we look at Noir's exploit again, returns back into the kernel, and the kernel eventually calls, return from syscall or so forth. But why don't we just call that ourselves? Why don't we implement that ourselves? So if we look at Linux again, it implements, returning to userland with an iret. The code itself is in entry.s. Very small amount of code. And that will essentially return us from a kernel context into a userland context. Where we return back in userland, totally under our control. We control the program counter that we return to userland. So, we don't really want the system call that we're exploiting, to continue working and, to write something to a device or something like this. We want it just to return back to userland, give us a shell maybe that's UID 0, and have the, the kernel run like normal. So, that's basically what I'm saying in this slide. I'm going to look at the exploitation of bin format conf.c a bit more. Basically, it's an arbitrary copy from user space, from disk, which is under our control. We can just write a binary and copies it to really anywhere in kernel space that's under our control. So all we do for this is create a binary that will execute a shell running as a super user, and we'll do that by doing our backdoor. We'll copy our backdoor into the kernel, start doing a set UID 0, and then we'll return back into userland, do an exec VE, and now we'll have a shell running as root. The code here I've talked about a bit earlier as well. The arguments are completely wrong. And now I'll go back to kernel stack smashing again. The important things I want to get across in the exploitation part. We have the kernel shellcode does not have to live in the kernel. Kernel shellcode can live in user space, in userland, running in the kernel context. So if we put our kernel shellcode that does things like set UID 0, that escapes a CH root, escapes a jail, so long as the kernel is in our userland segment, running in the kernel context, we essentially have the kernel running. So we don't need to know addresses within the kernel. We can point it directly back to user space and control it all from user space. That's pretty much the reason why we don't need addresses. We control user space completely. We can control all addresses in user space pretty much. We can mmap code to anywhere we want. We can return, if we overwrite the return address in a kernel stack to point to our userland code, we essentially have a kernel stack overflow where we control the address of this. At this point, back in our controlled userland environment running in kernel context, we can escalate privileges to a set UID 0 by looking at our kernel stack, looking at our task structure, changing the UID to 0, changing the GID to 0, and then at that point, we'll just return back to userland context. Again, userland totally under our control, and we can just return to another part of our userland program that does an exec VE that now is running a shell with UID 0. Okay, so this essentially is kernel shellcode without using offsets or addresses. It requires the address of our shell code in the sense that where we want userland to return, where we want the kernel to return to userland. So shellcode in this example would do something like execute a shell running as UID 0. But this is essentially the top of the code here just grabs the current task structure, and then from this we override our UID and GID with 0, and then after that we just return back into userland. That essentially is our shellcode there. Okay, I think I sort of screwed up the last bit of this presentation. It sort of sounded a bit obscure, but hopefully people will get something out of it, I hope. Okay, so one other thing about kernel stack smashing, sometimes it's not possible to overwrite the return address completely. Say for example we have a stack overflow in the kernel, and we can only overwrite the least significant byte or the most significant byte of the return address. If we control the most significant byte, we'll essentially return probably back into somewhere that we can control. We can mmap a lot of things. We can mmap code anywhere in userland. We can, for i386 Linux, anywhere below 0xC, 000000, anywhere below that. So all we want to do is return somewhere into an area that we can control. If we control the least significant byte of return address, maybe we can get it to return to another instruction that's already in the kernel that trampolines to somewhere in userland again. This is very likely actually. It seems that, can we find an instruction that trampolines back into userland? Remember that all we're looking for is a jump, a call, something that can get us into 3 gig of accessible memory. That's all we want, and at that point we can execute code running in the kernel context. Okay. I think I've been really confusing in that last part, but so what future work should be done here? I haven't actually written exploitation for SE Linux or UML to escape the sandboxing. I think that's something that I really do need to do. Okay, there are a lot of heap bugs with kernel memory allocators. I think this is more future work can be done on this, buffer overflows, double freeze, and so forth. Something that I wanted to talk about, I suppose, remote exploits. I've not actually seen any remote exploits in the stuff that I've audited. I have seen some bugs in things like the Coda distributed file system for Linux, And certainly there have been bugs in the past for the IP fragmentation code in most kernels. If I had to take a guess of where we would have bugs, and I do believe that there are bugs in the TCP IP stacks that are remotely exploitable. IP fragmentation code, the current Linux, I do believe has a bug in the fragmentation code. I was looking at this a couple of weeks ago, and it seems, which is, I have no idea why. When you have, Linux believes that when you have overlapping fragments, you should actually try to fix them. And that's a really bad idea in my opinion. So when you have two fragments and the first fragment overlaps the second fragment completely, it will delete the second fragment. And it will say, okay, the first fragment is authoritative, ignore the second fragment. However, if the first fragment not only overlaps the next fragment, but also the one after that, Linux will say, okay, delete the second fragment, but leave the third one and the first one there. So you'll end up with two fragments that are overlapping. And at that point, it will go to the reassembly code, and I'm not quite sure what happens at that point. I haven't looked into that, and it's something that I should do in the future. I think the IP options code also is certainly a great place to look for bugs, TCP options code as well. At one point, there was a bug posted to the Linux kernel mailing list with an IP options bug, and basically instead of filling the padding of the IP options with end of option, it would actually just overwrite the single byte with, it would overwrite the single byte and just ignore everything else. And after that, there was a bit of a rumor, about, is there a bug in the IP options code? A bit of talk on full disclosure and so forth. I think maybe this was related to someone reading the Linux kernel mailing list and saying maybe there's other bugs as well. The IP options code is quite hairy. I think maybe there might be things to do. For example, if you have options and fragmentation together, so you might be able to have an IP packet and fragment it and fragment the options so that your options might overwrite some adjacent bytes, but there shouldn't. There might be also some bugs locally with the options passing code, the options creation code, sorry. And also probably another place to look for bugs is kernel interfacing, the interface within the network layer. It's a good class of, everyone generally has interfacing problems when you have a lot of developers working on something. So that's probably another place to look for bugs as well. If there were actually things like overflows remotely, one possible way of exploitation would be simply to push shellcode into a userland process. That's all the kernel would do. There's probably a million ways to do this, but it seems like a very safe way. Create some shellcode that forks and does a connect back, and all the kernel does is find a process that's already running as a super user, push the shellcode into that process, and when the process continues running, it will fork and do a connect back in userland. So that seems to be a possible way of doing remote exploitation for that, which seems quite reliable as well. You don't really need to do any networking code within the kernel and just use regular userland code to do that. Okay, so that's pretty much it. Are there any questions? Okay, I hope everyone enjoyed the presentation, and if you want to talk to me afterwards, feel free. Thank you.